Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, welcome everybody. This is thank you very much for coming here and logging in to the network. It's a great pleasure to welcome Ed Knightley and Ryan, his student at Rice University, to Microsoft Research. Ed and Ryan have been working very closely with us on Whitespace networks, and this is a project that they've been pursuing for the last several months, and the talk is about the progress they have made and the updates they have for us. Ryan is a student at Rice University, a PhD student, second year. He has his bachelor's and master's from Johns Hopkins University fairly recently. Ed is a full professor at Rice University and very well known in the field. I know him best for this large deployment of about 4,000 users that he did in Houston, where people are actually using the mesh network that they deployed and built. Very accomplished, and all the bio is available to all of you. And so, without further ado, I guess I'll invite Ed to start it off, and then Ryan will carry it forward. Thank you.
Hit return. Will that?
Space.
Okay. Thanks very much, Victor, for inviting us. So Victor asked me just to briefly overview our group, so I'll just have one slide, and then I'll turn it over to Ryan for the main seminar. And so I just wanted to say what our group's overall projects are and the vision. And Victor mentioned the deployment in Houston, and I'll touch on that too. So what's been driving us in our recent project is wireless technology in underserved regions, and that's developing regions as well as urban underserved regions. And so this comes into three different parts. The first is, how do we deploy and experiment with new wireless protocols? And so the upper left there, I'm showing an FPGA platform that we developed at Rice collaboratively with a few faculty that allows us to completely clean slate design any protocol that we're interested in. So we're not bound to the current standards. If we have radical ideas, radical new technologies, we can implement it on the FPGA. The second part is integration with the applications, the community, and the clients. And this is also part of collaboration with other faculty. The lower left shows one of the families in the neighborhood that use our network. The lower right shows a health sensing device that monitors cardiovascular disease that we've deployed in the network. So we work with sociologists to do surveys to understand, anthropologists to understand the cultural impact of technology, and really make that link between what are people trying to do with technology and then what can we actually deliver. And then the final point is at-scale experiments. So we found it's very critical to get the urban propagation environments, the true user workloads, that we've gotten many surprises moving from labs and indoors and channel emulators and simulators to the outdoors. And so we've really integrated that as a key part of our methodology. So we have over 4,000 users in 3 square kilometers that access this network. The tower, we've installed a 60-foot tower. Those are all of our antennas. Our own access points use that tower. We have other nodes on top of tall buildings, and then others in the community. So overall, we've got about 20 nodes in the network, and much of the research that we're doing now has an experimental component on the tower or in the community.
Can I ask a process question? Like you said, you work with anthropologists and other scientists. Like, how does that come about? Like, do you develop technology, they go use it, or requirements flow back? And in what ways is your research getting influenced by that?
Yeah, so for the sociologists, we've asked them to do surveys of the community and focus groups and to understand how they're using new devices and how it's different. As an example finding, we did focus groups with teens in these neighborhoods. And we found that with mobile computing platforms, they use it very differently than higher income demographics. And the reason is higher income also have a PC. And so mobile phone is a satellite device to a PC. In these demographics, it's their main platform. People write, students, high school students write entire reports, do Google research on it, everything on the mobile phone. It's just really amazing how it's used. And so some of the usage, the features, they share it. Mobile phones are typically not shared in higher income demographics. So just to understand how do they use it, what are they trying to do, and what are their goals. And same with health care and trying to understand what the key monitoring requirements, what are the critical disease requirements, concerns, to focus on the right chronic diseases with those.
I'll have a very quick, I hope quick answer to the question. Two questions actually. One is that having done this deployment, how do you keep the network up all the time? Who's managing it?
Yeah, that takes a lot of money, and that's one of the downsides. We have a full-time network manager, and because nodes are programmable, then they just don't have the same resilience that commercial nodes would have. So it is a full-time job. Someone has to be there. Nodes go down. They have to physically be there, reboot, reset.
And people who are using it, do you find that they get unhappy, or I mean, how do they react to the network not being completely available?
Yeah, what we found is that in many cases, first of all, many are going from no internet access to this as internet access. So once they start using this, then they are very concerned. We've had kids on bicycles show up at Technology for All saying the network's down. Can you fix it? So when it goes down, we hear about it. On the other hand, we've also found people that once they understand internet and they start to value it and they start to buy PCs for their home and start to use it, then often they move on from this and they say, this is so valuable to me, I will buy a DSL service or some other service. Because we just can't offer right now the same rates that commercial offerings can.
And I guess the second question is that having deployed this and run this for so long, do you think, this is a question I get asked, and I'm going to ask you as well, which is, do you think mesh is all that it was touted out to be?
Yeah, maybe that's a dinner discussion, but I think that the hype was so excessive, and every mayor in the U.S. bragging that they would deploy the world's biggest mesh network, and that it would just revolutionize everything from poor broadband emergency services, you name it, that it was just impossible to meet that hype. So there are successful large-scale networks, Mountain View networks. Minnesota, there are many that are operating well and that are in heavy usage. Will we eventually see build-outs to the urban scale? I think that remains to be seen. But part of the challenge, and I think Ryan will touch on this a little bit, is the propagation challenge, that people want it in the middle of their house. They don't want to say, put an antenna near a window and then relay it in. It really makes a big difference whether you get in the house or not. And 2.4 gigahertz has just been a big problem to get in the house. And the low power requirements too. Okay, so with that, I will hand the rest of the talk.
I'll just make note. Here in Bombay, they installed 11,000 access points to cover a large portion of the city. What was this company? News company? Ruckus.
With mesh and with relay.
With mesh, right? Yeah, for the city.
Yeah, I think at one point Taipei had the record for the largest, but that really clips that.
Well, good morning, everybody. Thanks for coming. Just want to give you a brief overview of what we'll talk about today. We're going to give you a little background of where we're coming from. I think Dr. Knightley did a good job of that. Introduce the white spaces. Most of you are aware of this, but this is just a brief overview of our understanding of the white spaces and some of the challenges of working in them. Talk a little bit about the work in there. And we'll present to you a couple system models that we've come up with at Rice to try to analyze the performance of networks built with these and compare and contrast them with traditional Wi-Fi networks. And then I think finally what we want to do is we want to show you some ideas that we have for the future of what other future applications of white space might look like. So let's get started. So the goal, as Dr. Knightley said, was that we want to build a low-cost urban Wi-Fi network to serve the underserved communities in a very low-cost manner. The cost is going to be the main performance issue here. And the challenge that we've seen with the Wi-Fi networks of the past, the reason why they didn't live up to the hype, is for a number of reasons that we've experienced as we've deployed a network in a neighborhood ourselves. There's a lot of problem with the short propagation waves or distance of Wi-Fi radios right now. It's not necessarily big enough to make a robust mesh network in a neighborhood. The spectrum is congested. We see other people, other devices, other networks popping up on top of ours, competing with that transmit time. And so we're working in a spectrum that's been being used by a lot of free Wi-Fi devices. So we'd like to open up more bandwidth. And the other thing is, as people use more and more media-intensive applications, we need an additional system bandwidth than what we have now. So if we think the problem's bad now, it's just going to get worse in the future. And so one of the questions that we want to answer today is how does white spaces change the equation? How does it make things better for us? So just real quick, the white spaces, as we know, are the unoccupied TV channels. And to give an example, we did a measurement at Rice University with a spectrum analyzer. So this is the power distribution over the UHF band, TV band, at Rice University. And you can see that a number of channels are obviously occupied. Every one of these numbers refers to an air channel used by broadcast TV services. And the idea behind white spaces is that if there are unused channels, let's use them. Now, this is a little deceptive. Under some conditions, we would call these channels unused, but the FCC has a different definition, and so we'll get into that right now. So the FCC has recognized that there's a large amount of free bandwidth available that's not being used that we can free up to other people to use. And so they've allowed unlicensed access on these unused TV channels, provided that you can prove that you're not interfering with TV reception for the users that are receiving TV broadcasts. And so their thinking is that you have some contour, some area where you would normally be expected to receive a broadcast from a TV station. If I have my white space device that has a certain interference range, I don't want to interfere with any users in that area. And to that effect, they've come up with a keep-out range above and beyond where you would normally expect to get TV reception that we need to protect. Because if we move, obviously, inside of it, then we start killing TV receivers inside that reception contour. So we want to stay out of that. And so that's the motivation behind sensing. Yeah?
This keep-out range is signal power or distance?
You can relate the two to each other if you have... so as you go further and further away, if you say, I want to protect signals.
How does FCC specify it?
So the FCC specifies it as saying that if you sense a TV channel at a receive power of negative 114 dBm, then you are not allowed to use that channel. It's considered occupied, and you cannot transmit on that channel, and the power that you transmit on in adjacent channels is reduced from normal levels. And so that's a pretty intense restriction, and we'll see how that plays out later. The other thing that has been mentioned before is that we also need to protect wireless microphones. So there are a number of incumbent microphones that are already using unused TV channels for talks like this. It's a much harder technical problem to sense these microphones. And we're not going to discuss that in this talk, but I just wanted you guys to be aware of that. So operating as a secondary user in the TV white spaces, it means that we're only allowed to use spectrum on an opportunistic access method. So we don't know what spectrum we're allowed to use and when, and it's going to change as time goes on. So we need some sort of awareness, some cognition of what's going on. So that ties into the whole cognitive radio field, where we need to know who's transmitting where and what we're allowed to use. So to give an example, the group here at Microsoft has made, I think, done a pretty good job of addressing a lot of these concerns. They've demonstrated what they call the NOSE platform. It's a prototype cognitive radio operating on the white spaces, and they've demonstrated to the research community, and more importantly to the FCC, that you can reliably detect these primary TV users, and you can protect receivers from your transmissions. They've also demonstrated a MAC that allows you to bond that non-contiguous spectrum together and sort of treat it as a point-to-point link. And I think a lot of the work that they've done has allowed us to treat a white space link, taking all those problems that we have with sensing, acting as a secondary user, and sort of abstract that and treat the link as a better Wi-Fi link. And so that's very powerful to us. The other group that has been working in this area is the 802.22 group. So similar to 802.11, they have similar in scope. They have come up with the first universal cognitive radio standard that everybody in industry can get behind. And so there's a lot of provisions in there for centralized scheduling, coexistence of different radios, different networks on top of each other, and standards for spectrum sensing. So that's very interesting. But one of the problems with their approach is that right now there's no notion of mobility. Their current understanding of the white spaces, or their current goal, is to develop a standard for this single application, acting as a backhaul to homes. So their idea is that you have a large station that covers a large area, and everybody who's a user has a large directional antenna on top of their roofs. And that just acts as a backhaul and then connects to the home network. So that's their only focus right now, and there's no intention for the first drafts to address mobile situations or anything like that. And the last point is that there's a deployed network with real users deployed by a company called Spectrum Bridge in rural Virginia, and they've just showed a point-to-point backhaul link, very similar to what the .22 group expects. And so I think these are some of the big contributors to this field right now. But we'd like to take the next step. What can we do with white spaces? How does it, if we were to swap out Wi-Fi with white space, how do things get better? So we want to answer these two questions. Does the use of white space change the cost structure of urban scale Wi-Fi? If we swap out the Wi-Fi links that we have now with white space links, how do things change? And then later on, we're going to answer this question of what new architectures can we build using white spaces. And so to start at the beginning, the main difference between the two technologies is that we know that the range of your radio for a given transmit power, for a given receive detector sensitivity, has a strong dependence on your carrier frequency. So just to demonstrate here, for a given transmit power and antenna gain, and you can see that white space point-to-point link over free space goes much, much further than what we've been able to do with Wi-Fi devices. Now, I want to clarify that this plot right here incorporates some expected receiver gains that we would expect with white space over receivers in 2.4 gigahertz. We expect a slightly lower noise floor, and I've talked to some people about the hardware behind that. So that's incorporated in this graph. So this is what we're seeing here. And the other question that people ask me is, what is this best and worst? So when going from 2.4 gigahertz to the white spaces, which we said we're operating at 50 to 600 megahertz, it's an order of magnitude change in the frequency. And so we see that in the two different radiuses that are plotted here. And so the different TV channels that we could operate on, the maximum range that we could get with those is somewhere in that spectrum, somewhere between the best and the worst case. So when you plan a network, you might have to consider that operate on different channels, you actually have drastically different propagation distances. Whereas in Wi-Fi networks, that's just it's so negligible going from different Wi-Fi channels to not even consider. So to take a look at to analyze this network, let's introduce a simple model. So we're going to look at a simple one-hop, what I call the cellular model. And the idea is that we have, we're going to model the coverage of every one of our APs as a hexagon on a plane. Yeah?
Quickly ask a clarifying question. What aspects of cost are you going to consider? Like, it seems this is, depending on how you want to tackle it, this could be a red herring. Like, who knows what the cost of equipment is going to be? That's kind of tied into volume discounts and whether you're trying to operate a for-profit network or not, and things like that. So what aspects of cost are you going to consider and what?
That's actually a really good question. And so let's show the rest here. The measure that we're going to look at, and I think this is a fair measure that you can later take cost arrangements that you mentioned, is we're going to look at the amount improvement in the number of deployed gateways, number of deployed APs to achieve certain network goals. So we'll get more into detail, but we're going to look at if I can deploy, say, 50% fewer nodes with a Whitespace network, that means to break even, the cost of a Whitespace AP has to be 50% less than a Wi-Fi node. I'm sorry. It cannot be more than twice the price of a Wi-Fi node. Yeah.
Since range goes down with frequency, did you look at VHF TV frequencies?
I'm sorry. Range goes up with frequency.
Goes up.
Yeah. Let's go back. Sorry. So the inner circle, this worst case for white spaces, would be the UHF frequencies, the very top of the UHF frequencies, so 698 megahertz. And the VHF starting at 54 megahertz is the outermost. Yeah.
So, sort of to follow up on those question, there is one other variable, right? You have to at some point of time consider the throughput people get, because people care about range only in a very abstract sense. Once they're connected, they want some reasonable throughput, which potentially could be much lower or much higher in a white space network. And that has to factor into the equation. Depends how many different access points you have provided, right?
Yes.
It's not a question of just range.
Yes, it's not a question of just range. And actually, one of the things that we'll look at here is the size of our cells here are determined by the distance that you can go before your performance drops off to a point that we consider that not a good connection.
How many users share that cell, do you expect?
We'll get to that. That'll be the next 2 slides from now, and we'll answer that question.
I'll just make one comment on the cost, because the way I sort of think about it, I think cost of an AP is a non-issue. We just take it as zero, just like we think cost of the Wi-Fi is zero. I think that's not something that's going to be a problem at all. There's nothing inherent about white spaces which can bring the cost down to $5.
I think fundamentally you may be right, but a cellular base station is really expensive today.
But the reason for the expense is not the equipment is part of it, but the reason for the expense is the operator cost, which is the maintaining it up, putting it up, buying all kinds of towers, all that sort of stuff.
To speak,
even once you buy it from Lucent or whoever you're buying it from, like you're forgetting the operating cost, just the acquisition part is expensive.
There's no commodity. See, that's the thing.
Yeah. To speak to that.
So that's where volume.
Yeah, that's what.
Yeah.
So it's not a red herring in my opinion. It's sort of like saying,
No, it's red herring for I think what he was trying to do. So I just wanted to clear that he's going to ignore that and not make claims because that.
Yeah. No. What the goal of this is to say the reason why we're even looking at this in the first place is that we can consider it an ISM band. It's unlicensed. And as you saw the explosion of devices and services that operate on Wi-Fi, on the Wi-Fi band, and the reason why Wi-Fi is a commodity is because it's unlicensed. Anybody can use it. Any manufacturer can make a chipset within certain bounds, and that brings the cost down drastically. You don't have to buy the spectrum. You don't have to deploy the towers. You don't have to pay somebody to build custom hardware for you, and that brings the cost down. And we would expect the same process to apply to white spaces eventually. And so when we're looking at cost, we're going to look at this output variable here, the number of required gateways. And so if you say that right now the economy of these systems are such that white spaces cost twice as much, or a white space node costs twice as much to deploy, right? To build, deploy, operate. Then that means that if you can bring down the number of nodes that you need to deploy by half, then you've broken even. So any other improvements means that the cost has just shifted in towards white spaces. And this number will be good no matter how the cost changes, how much the relative cost changes. Yeah.
Just curious, in your current deployment with Wi-Fi, what's a typical utilization of a backhaul link access?
Very high. Very high. We hit saturation.
Oh, really?
Yeah.
Is it because the links are low capacity, or is it because people actually use it a lot? I mean, you can saturate a 1 Mbps
Yeah,
link and that doesn't mean
it's a mix. The access links are always 11 megabits.
Okay.
The backhaul links, once it's aggregated, are up to 54 with 11A. So it depends. But yeah, it's very highly utilized. And maybe just one other follow-up point on the cost issue. For us, the install cost of the node, the person actually to go there and for either assemble the tower or go up on the roof, align antennas, all of that overwhelmingly dominates for the cost of the node.
So within that framework, this is how we're going to analyze the network, and we'll introduce something new later on. But let's take a look at what this looks like. So before we continue, there are a couple of things a couple of considerations that I want to introduce. The idea is that we want to build our network to provide a certain amount of service to everybody in the network that can connect. And we can do that today by essentially deploying more and more nodes. And so our measure is area capacity. How much capacity per unit area can I provide users in my network? And we can essentially play games where we decrease the transmit power of our nodes, shrink their coverage area, and deploy more nodes in an area, and so we've increased the area capacity. But once we start doing this, our network starts getting more and more expensive. The cost to deploy this network on the left is 1, and the cost to deploy it on the right is 7. So we've gotten 7 times the gains, but it's 7 times the cost. This is not interesting. We can play this game forever. So actually, a more interesting measure is looking at the maximum cell size to provide a certain degree of service to our users in the network. So we'll see how that interacts later. A couple more assumptions that we need beforehand is we're going to look at broadband users. How many broadband users can we support using this definition from the FCC of what a broadband user is?
It's going to change, by the way.
Yeah.
In February, they're going to come up with this. This month, they're coming out with a big notice of what broadband needs, and this is going to just throw it out.
That's true, and that actually motivates the third model we'll look at today, where we try to do away with all of these hard numbers and try to look at some very fundamental measures of system capacity. But I think this is a good way to introduce these concepts. The other thing is we assume some oversubscription factor. When you're provisioning a network, you say not everyone's using all the bandwidth all the time, so we can add a factor of 40. And the .22 calculations, provisioning calculations, use this number, so we'll use it here. The other thing is one of the primary environmental factors is your path loss exponent, determining the propagation distance of your wireless signal. And so we've measured this directly at TFA. It's about 3.3. So consider that an environmental parameter that we've measured, and we're going to use our TFA network, the network that we deployed in Houston, as a baseline for that.
Do you think that'll hold for lower frequencies now?
That's actually an interesting question. And I think
Probably not hold, right? We talk about things getting through the walls and everything else. So frequency maybe, I don't know, may not hold.
yeah, and we've actually looked
So
at
the point being conservative, right? You actually can come out ahead.
yeah. Some models do include some models of propagation for different frequencies include correction factors, and we do look at that in our research, but we're not going to present that today. It's a lot of stuff to go through. But it is an interesting question. But I think that these models provide the framework. Given that number, we can tell you how your network will perform. And then the last thing is that we're going to assume that the spectral efficiency of our systems are similar to what we see in Wi-Fi with a Wi-Fi card. Current prototypes use Wi-Fi cards or similar hardware. Just a note is that the .22 group working on the standard expects the spectral efficiency to be about 2, much lower than it is right now. So this could be an optimistic viewpoint. Just wanted to make that note. So let's take a look. The way that I think the best way to visualize the range of networks that we can deploy is this, what I call a capacity region, network capacity region. And the idea is that for every type of gateway or every type of network that we could deploy that looks like this, there is a certain gateway density and client density that defines that deployment. So for the gateway density, we can provide a certain degree of service. How many clients can we support with that network? And so the colored patch here is all the networks that are feasible given the assumptions that we just talked about. And so just some comments about this is that, like I said, we can shrink these cells down as much as we want, increase our gateway density as much as we want, and we can serve as many people as we want. That's not interesting. We can play that game forever and our deployment costs go up. So that's not interesting. We're more interested in these two boundaries. This leftmost boundary, which is determined by the maximum propagation distance to provide service. And as you change factors that change that maximum propagation distance, say transmit power, things like that, this is going to shift. And this other boundary, which is determined by the maximum data rate you can get over a link. If for a given system, if you can send more data over a link, then obviously you can serve more users. And so the way that this changes as you change the parameters of your deployment is that if, say, I reduce the receiver sensitivity 3 dB, I shift the feasible area, that boundary, to the right. And if just going back, something like that. And if I do something like half the capacity, the available bandwidth to my system, I bring down the number of users that I can serve by about half, by exactly half, actually. So this is a good way to compare the four different technologies that we're going to look at here. And this is what it looks like. Using the available bandwidth, Whitespace bandwidth, at Rice University, which happens to be 2 VHF channels and 5 UHF channels. We've plotted these network capacity regions for Wi-Fi in magenta, Whitespace in the UHF band in blue, and Whitespace operating in the VHF band in red. And then you have a Wi-Fi operating at 5 gigahertz in green. And so the main features that I want to point out here is this unique area to white spaces. That we can deploy a network that serves a low number of users with a very low cost in terms of deployed nodes network with white space that we could not do with Wi-Fi. So that's one of the advantages of white spaces.
Questions. What transmit power are you assuming and what receive sensitivities are you assuming for both Wi-Fi and white space? Because people who are going to build white space devices are going to say, okay, minus 114, what if I apply minus 114 dBm to a Wi-Fi? I'm going to increase the range that way, right? And white spaces, on the flip side, white spaces actually allows greater power, so you're going to have very low level white space.
Well, I'm sorry, what do you mean by greater power?
Well, you can go up to 4 watts, right? White space current to ceiling, whereas you can't do that for Wi-Fi.
Well, to my understanding, you can go up to a maximum isotropically emitted power of 4 watts. And you can do that in both bands, to my understanding. At the upper ranges of 5 gigahertz, you're reduced to...
5 gigahertz, you're not allowed to use.
No, you're not. Outdoor, you're not allowed to use that. But at 2.4 gigahertz, you are allowed to transmit at 4 watts. So the comparison between 2.4 and white spaces, in this particular case, are pretty close.
Okay. And what about receiver sensitivity?
So in this case, we're assuming we're using. Remember, I showed you those circles of coverage, and we included some expected gains in the white space receiver. We've been building TV receivers for many years, so we have a lot of experience building good receivers in that frequency range. So we're using a conservative Wi-Fi receiver sensitivity of 85 dB and white space receiver sensitivity of 100 dB.
Okay.
And those are based off some of the numbers that you guys have experienced with your...
I know.
Yeah.
In some sense, it's kind of unfair because I should have brought this up earlier, but nevertheless, I was thinking about it as you were presenting that perhaps a good comparison would be to keep the receiver sensitivity similar to, because there's no reason why you can't do the same thing in different bands, right? Yeah. So that'll just, we'll have to see how that plays into it.
Well, actually, we can conceptually visualize how that would look, and I know for a fact that it looks this way. But remember that we said that anything that changes the maximum propagation distance of your wireless signal would shift that leftmost boundary to the right. So we can take that white space, it goes all the way almost down to the origin there. We can shift that, and it goes to about 1, somewhere around there. I think it's actually a little bit lower, so maybe like 0.8, something like that, if we look at a receiver sensitivity of 85. And so this framework gives us a way to analyze any changes that even I haven't thought of that change those two parameters, your maximum link data rate or the maximum propagation distance. And so we're looking at, for a very specific case, what we would expect if we deployed a network right now in Rice. But you can imagine that there are a lot of scenarios that we haven't even anticipated. And this is a good framework for analyzing that. So to get back to this, we've said that there's this unique capacity region for low performance, low density networks. And when I say low performance, that's not necessarily a bad thing. Maybe we don't need all this additional capacity. We can deploy a cheap network with white spaces that we couldn't do with Wi-Fi. And keep in mind that this is just for the Rice University or Houston area environment. It might get better some other places, and we'll see that it does. And like I said, 2.4 gigahertz would win if we needed a high capacity network. If we needed to serve a lot of users, we would have to deploy a 2.4 gigahertz network like we have right now. So let's take a look at another network deployment. Let's take a look at a 2-hop deployment. So this is more similar to what we have deployed in TFA in our network in Houston right now. It's a 2-hop network where we have gateway APs that are directly connected to the wider internet. We have relay APs that serve as a relay between users and your gateway. And just to illustrate this in another way that might make more conceptual sense, this is what it would look like. We have these APs on towers. We have a gateway that's connected to wireless internet. And we're going to assume that there are 2 radios on every AP. One radio serves as a backhaul, just for communications between relays and gateways. And the other radio, it serves to serve your clients. And so we're going to assume the same parameters in the first case, that we're dividing our frequency into 3 non-overlapping channels. And we're doing that on the small scale for the client access, these colored hexagons. And we're doing it at the large scale. These groupings, clusters, are also dividing their available bandwidth so they don't interfere with adjacent cells. And let's look at the capacity region for this type of network, what that looks like. And so now we have all different pairs of technology for the client on the first hand and on the backhaul link on the second number. And so I ran out of colors. And so to clarify, I thought it would be nice. The worst performing is the bottommost, 2.4 and 5. And that's this region over here, high cost deployment. And the best performing, which is the 2.4 Wi-Fi on the access link and white spaces on the backhaul. And that's that yellow region down there. And you can imagine that all of these extend all the way to the right. And so what we see here is that, again, we have these white space backhauls. If we use white space on the backhaul, we enable these low density deployments, all those regions on the left-hand side that you can't get with a Wi-Fi backhaul. Yeah?
No, this is for propagation with unidirectional antennas.
That's correct.
So would that necessarily apply to the backhaul, where you could imagine that you'd have all your backhaul links would be set up professionally by people who can aim a directional antenna?
Mm-hmm. That would definitely look different. And I think that's if we were trying to analyze the network that we have deployed in Houston right now, for us, we're using some directional antennas, but we're not using them in this sense. We're treating them as additional gateways. And so when we use backhaul in the TFA environment, we're actually just using omnidirectional antennas. And one of the things that we found out when we were deploying our network and servicing it is that directional antennas, they become misaligned. They're very tricky. You have to serve them a lot. And in a lot of cases, it's much nicer to sort of deploy and forget a network with an omnidirectional antenna and have them sort things out on their own. But you do bring up a valid concern that this model is for an omnidirectional antenna. So we're not looking at directional antennas in this particular case. Yeah?
How much freedom do you have in terms of where you place your backhaul transmitters and receivers? Or are they sort of co-located with customers, or just like how cell tower companies go out of their way to find the optimal location for placement of cell towers?
That's actually interesting. We've had a number of our other students address that sort of problem. And the models that they came up with, they found that often you don't really have a choice, a continuous choice of where to deploy your nodes. Often you're limited to, I can only deploy nodes on, say, light posts. So wherever there's light posts, that's a potential node location. And if I'm deploying a node there, for cost reasons, I might as well deploy a relay and an access radio at the same time. And so that's very common, and most commercial products do that, co-locate those two radios. Yeah, so this is interesting. So this is what it looks like at Rice. And just to point out some features, again, we have those low density deployments that we can get with Whitespaces. But if we were to deploy a network at Rice right now, we would choose sort of that magenta region if we wanted a high capacity network. And that involves just Wi-Fi technology, 5 gigahertz and 2.4 gigahertz. What's more interesting is, that sounds very bleak, but now let's say that we have more Whitespace channels available to us. So let's double the number of Whitespace channels available to us. So this is the situation that you might see in a more rural area, or a small town, city, something like that. Sorry, small town. So we've doubled the number of channels available to us. And when we do that, suddenly these Whitespaces starts to look a lot more attractive. And so again, now if we were to deploy a network, we choose that leftmost yellow region and green. So yellow region for a low density deployment, and green for a high performance deployment. And both of those use Whitespaces for their backhaul, because Wi-Fi just doesn't have the distance or capacity to act as a good backhaul. That's what we get over there. So we can get much better performance with Whitespaces if we have the available bandwidth. So that's a theme that we're going to see recurring over and over again. One other thing that I wanted to mention here that's particularly nice about this setup is that if we use the best deployment in the right-hand side is a deployment with 2.4 gigahertz Wi-Fi radios on the access link, and Whitespace as the backhaul, which means that from the user's perspective, we've hidden all of the uses of Whitespaces. So anybody with legacy 2.4 gigahertz devices can access this network. And so I think that's very interesting in terms of deploying a network that people will use, is they already have all these devices that automatically work with this. And that's the best deployment that we can make using this model. And so the last thing that I wanted to get to is that we mentioned that a lot of things change as say the parameters of our equipment changes, as the receiver sensitivity increases, decreases, I don't know, as new innovations in building radios comes along, and suddenly the assumptions that we've made are no longer true. And so the next model that I want to show you is based on information theoretic capacity. So rather than saying the number of users that I can serve, I'm going to look at what information theory tells me theoretically what is the maximum amount of capacity that I can supply my users in terms of, say, megabits per second per square area. And so we're not going to depend on the hardware parameters that we talked about in the beginning stage. And we're going to be able, using this method, we can incorporate a lot more real-world effects that we see in a network. We've things such as so this is the equations that we're using. This is the information theoretic capacity, Shannon capacity of networks that are used to come up with an upper bound. What's the best performance that we can get with a network theoretically? And so this is what we'd like to attain. And so we model the signal to noise ratio at your receiver and your AP, and you get a capacity based on that signal-to-noise ratio. I don't want to go too much into the math, so those of you who know about this equation, Shannon capacity, this is what we're using here. But like I said, we can incorporate more real-world effects, things like asymmetric upload-download rates, asymmetric transmit-receive, fixed and mobile transmit powers, things like that. So we can incorporate an AP that transmits at 4 watts and a mobile unit that transmits at 100 milliwatts. What's that? Alpha would be a parameter defining the portion of airtime spent on an upload, and 1 minus alpha would be just the reverse of that. Alpha is the amount of airtime spent on a download, and 1 minus alpha is the portion spent on upload. And so we can look at how the system reacts to different measures of alpha. We're not going to look at that here in this presentation, but it is looked at in the work. Just to give you an example of the more real-world effects that we can incorporate with this model. And the nice thing about it is that we've decoupled our results from the assumptions of what hardware we're limited to. So these are the best that you can do. So this is what we get. So this plot, I'll walk you through because it's a complicated plot, but I think it tells us, I think it drives home the point that we're trying to make here today. Is that on the x-axis we have the number of free whitespace channels available to us. So we're going to increase the number of whitespace channels that we can utilize. And for a given number of whitespace channels, what is the minimum number of nodes, APs, that I can deploy to satisfy the demands of all of my users? And so in this case, we're assuming that users are uniformly distributed in a plane, and that all of those users collectively demand 100 megabits per second per square kilometer. And so this is just a measure of capacity. You can translate that into number of users as your requirements change. As the FCC raises the bar for broadband, this number will still hold true. So this is going to allow us to make a fair comparison between whitespace and Wi-Fi. And so we've plotted what this looks like for a number of different frequencies. And so the first three, 54 to 698, are the whitespace frequencies. And the last three are the different ISM bands. There's a small amount of free bandwidth at 900 megahertz. This is just plotted here for completeness. And so just to walk you through this, as we increase the number of whitespace channels, obviously the amount of bandwidth performance that we get out of a Wi-Fi network doesn't increase because we're not using those channels. So the only thing that changes is the performance that we get out of a whitespace network. And so as we have more and more bandwidth available to us, the cost of a whitespace network decreases. So in this plot, lower is better. And you can see that there's a certain crossover point where suddenly whitespace goes from really, really non-attractive to us in terms of cost to very attractive. And just to put some numbers onto that, here's a percentage gain of whitespace over 2.4 gigahertz Wi-Fi. So that the more fair comparison, as I said, is 2.4 gigahertz. And so this is the percentage gain in number of deployed nodes. So again, like we said, this is analogous to cost of your deployment. And there's a crossover point at 0 where if we have 3 or more whitespace channels, our network, we can deploy fewer nodes and serve our users at 100 megabits per second per square kilometer. And as we even get more and more channels available to us, our performance gets even better. We can deploy anywhere from 60% fewer nodes to 80% fewer nodes on that ballpark range. So this, down at this range, that's very optimistic. That's a lot of available bandwidth. And we might not see that in every location. But you can see the potential gains if we have that many channels to work with. And they're out there. If TV broadcasters aren't using them, we can. So this is the potential gain that you get from using white spaces. And this is going to change, bear with me, as we've said that clients demand 100 megabits per second per square kilometer. Now, as we go to next generation media demands, that might not be enough. And so as we increase the demands of the users by an order of 10, the trade-off shifts. So this crossover point shifts over to the right. So now we need, rather than just needing 3 to start to beat Wi-Fi, we start needing 7 or more channels to beat Wi-Fi. So that's still interesting. But again, as we go to a high degree of available bandwidth, we can deploy a network with 60% fewer nodes. I think that's a pretty good argument.
In concrete terms, how does it play out like in urban versus rural areas? So in rural areas, you will have lower client density but more channels. In urban areas, exactly the opposite. So does that actually work in your favor or against it? Like, I'm having a hard time figuring that out.
It's interesting. So as you shift to a rural area where you have fewer clients and more available channels, the performance of a Whitespace network is going to go up enormously. So it's win-win in both degrees. As you look at
That's what I thought as you were asking the question, but there is a trick here, right? I mean, the average distance between a base station and a client is going to be higher in the rural area.
Yes.
And that means your link capacity, link quality is going to be poorer.
But at the same time, if you have a poor, so let's analyze that. That's true. As you move the nodes further away from each other, your link quality decreases. But if you have more bandwidth available to you, you can send fewer bits over each channel, and you can still maintain that connectivity as you could before. And so that's the advantage of having more bandwidth available to you. I mean that's obvious, but this tells you exactly where the trade-off is.
This is really important result. I mean, this is why we wanted to do it. And the reason, as you know, I'll just repeat it for people here, is the reason is that we're struggling to convince SEC that wireless microphones should not be made as primary users. And the problem is, if you make them primary users, you lose the channels. If you lose the channels, you basically lost the whole game completely. And so we will probably call on you to give a presentation to people who actually have to run through this very carefully.
Yeah.
You're trying to say who shouldn't?
So what's going on is that so SEC has allocated rate, and so there's a bunch of channels, as Ratan asked, in the urban areas like Los Angeles and New York and stuff. There are very few channels available. Now the microphone lobby has been saying that we were here first, so we should become primary users. Primary user means that those channels that they operate on are gone again. And Microsoft's position has been that we are fine with certain license use for microphones like NFL and games and Olympics and all that stuff, but the predominant number of microphones either have to move out, which are because they're actually illegal, or alternatively, they have to behave just like Whitespace devices, which means they're secondary users and they will try to get the thing as well. And the point I was making now with his graph and with this actually shows that if you don't have enough number of channels, then it's a non-starter. And if it's a non-starter, nobody's going to invest in actually building these devices out. So the SEC needs to be convinced that these numbers are sort of important, and we need a certain number of channels to be free in every area for this to become actually much more. It's a much more concrete way of saying rather than saying it in a fluffy way, which is saying, yeah, more channels is a good thing.
Especially given the comment about the bandwidth problem.
Yeah, what was this?
They made a comment again that you're going to run out of bandwidth like very, very soon.
Yeah.
This government had a press release, and it's fascinating because I keep trying to think of, can you even today broadcast just on a mobile space? Can you broadcast a live event? You'd run out of cell, number of users per tower will go down to like maybe 200 or 300, which is ridiculous now. You high bandwidth broadcast.
Yeah, we won't be able to do any of the video stuff that people talk about, given what we have.
That is impossible today. Right?
Yeah, and we are in 2010.
It's getting worse, if at all, right?
What happens in 2050?
Yeah, that's a good question. What's the 3G capacity?
I'm sorry, say that again? I missed the first part.
What's the comparable 3G capacity?
I'm sorry.
3G.
That's a good question. I don't know. I haven't looked at that explicitly. My focus was comparing unlicensed spectrum, but that's a good question.
Spectral efficiency or capacity?
No, on this graph, if you were to compare 3G, what would it look like?
Somewhere between, right? Based on this, so this is entirely based on frequency.
That's right.
So it's just between somewhere.
Yeah. It also depends on how much bandwidth is actually available, right?
Yeah, they have like 50 megahertz, right? They got more through the auction last year. So depending on the area, it could be more.
But the question is really important because they are asking that the white spaces that are unlicensed be released to them for purchase.
Right.
Yeah, and so that question becomes relevant there. They can say that we can give you better capacity if you just let us purchase the stuff.
I think that's the biggest risk for me, like that completely change the way the U.S. networking industry at least works or doesn't work great for the next couple of years.
Yeah.
It's a really crucial question.
If this bandwidth becomes licensed, then I mean the whole assumption that we could deploy cheap networks goes away.
Or pseudo-licensed, right? It may
What's
not
that?
It's or pseudo-licensed.
Pseudo-licensed.
Yeah, like there are two. One is really licensed. The other one is just that you make it inaccessible for any normal, like low-end manufacturer, like you said, to be able to create these devices and proliferate them.
You even put some rules around.
Yeah, you put some rules
for.
Exactly.
Yeah.
So be careful when you bash 3G as an expensive technology, because I mean, yes, it is. It costs the operators a lot of money to deploy individual cell towers and so on and so forth. But look what they've done in places like India. I mean, they've brought some minimal data connectivity, even if it's just text messages and phones, at like dirt cheap costs. So from the consumer's viewpoint, it is cheap, right?
No, it depends on the definition of your broadband.
I agree.
Broadband, right?
Yeah.
So, I mean, what you're talking about is true, but you look at the services that are being provided are not the broadband services that the U.S. wants to provide to every average user.
Sure. I agree.
Maybe I'm repeating the previous question. If, from what I read, the first broadband server was a Japanese I-mode phone, which was 9.6 kilobit per second, but always connected. What was happening you designed for that?
So very low bandwidth.
Well, the 9.6, I mean, I've seen 300. I've done work at 300, so 9.6 is not so bad. But 9.6 always connected. Would that change your numbers?
That would shift us towards, so these numbers are the same no matter how much you're allotting per user. So these numbers of 1,000 megabits per second per square kilometer, you're just divvying it up among your users differently. And so that's the nice part about this model of looking at information theoretic capacity.
But of course, at that per user bandwidth, they are standing next to each other in a football field.
Oh yeah. And naturally, I mean, you want your network to be over-provisioned to handle spikes in traffic, things like that. Yeah, that's true. If that's true, then rather than say operating at a very high capacity, deploying a high capacity network, you deploy those nodes more sparsely and you provide people with a slower data link, something like that. And so you save cost in the deployment, but your performance is lower. So we've shifted from those network capacity plots that we showed you. We shifted from the right side to the left side, that very low density, low performance network, which we can now get with white spaces. So maybe in India, this might even be, so they think that's dirt cheap, we might be able to do even better.
Well, actually, the will stuff is really interesting in India, right? Like I was going through some rural areas, and there are a lot of people who actually started using the wireless and local loop stuff that Tata popularized, because it's the only viable bandwidth that's available to them. The 2G bandwidth that's there currently can't really serve. I think people are getting more sophisticated, like even the rural areas, like with the computers. Nice to see video. So there's this interesting conundrum there. I think that's shaping up now.
I think that should be interesting, because if you start using unlicensed devices, then rather than depending on a carrier to deploy the network and then sell you the handsets and then provide you a subscription, which might be very cheap, now the communities can take that power into their own hands. And that's sort of the idea behind what we do at Rice, is that the community could deploy a single AP in the middle of their town, and everybody could one time buy a receiver that works for as long as that network is there. And so that changes that relationship a lot. So that is interesting, and that's definitely a opening for research.
I don't want to take you too much off of your talk, but places like India and Brazil and all these, they don't even have this notion of opportunistic networking that we're struggling with here. I mean, they have some frequencies available, and they don't know what to do, and they say, okay, use it or whatever. So
yeah.
The thing here about number of channels and all is very particular to European countries and to the U.S. And we don't know, like in China, for example, they have this broadcast industry which says they own the whole spectrum, and they're just saying, use it, but in fact, they're mandating, do it for interactive TV or content-based stuff.
The thing that keeps worrying me here a lot is the guys who are running up against the problem to take a lead in this today are very quickly becoming the mobile operators. Again, if you've used an iPhone in LA or San Francisco, forget Seattle. Seattle's good actually, or New York, LA, or San Francisco. And even with LTE, my bet is that doesn't change. right? Because the number of phones are ramping up too fast compared to the deployment speed. And they're running out. So the next logical place they'll go to is this, and that worries the hell out of me if they go first.
Yeah.
And they have lobbying powers too, well beyond what we actually.
That's true. That's true.
It worries you in a business sense or in a technical sense?
Both. Like what you can enable when you have Wi-Fi versus 3G, right? Like, let's say your use of spectrum was metered and governed like for the last 15 years. You couldn't have popularized a lot of things that are popular now.
Yeah.
As software providers, I think it's really important for us to see what the limits are, because software is connected now. You don't have unconnected software, so yeah.
So yeah, before you finish up, there's well, not one last thing, but one last concept that I want to introduce. What does the future look like? What is it going to look like going from here on out? And we have some ideas of interesting networks that we can build. So just to review so far, we've just discussed this, so I think we can go over it quickly. I've presented you a bunch of models that you can use to predict the economics of white spaces. How many channels do you have? Okay, this is the types of networks you can deploy, and this is how much they're going to cost you in terms of deployment costs. And so we've seen that in some cases, yes, white spaces win out, and sometimes drastically so. And so at the same time, we need to be aware. We can't promise that white space is going to solve all of our spectrum woes. Particularly in a city, we're going to run into issues with available channels. So a smart application of white spaces is definitely in order. You don't want to make these grand claims that Wi-Fi did in the past about meshing and then not be able to deliver. So tempering our findings in the first part with this understanding that the number of channels is going to affect that trade-off point is very important, I think. But again, there's a lot of promise for covering rural areas, which are the areas that I think the broadband stimulus package is focusing on. So this is, I think, a very interesting area for that. And again, some cities where there aren't a lot of incumbent TV transmitters, this might be great. It's a matter of understanding your environment that you're working in. And now the last question that I want to answer is, can we use these white spaces to enable a new type of network? And so let me show you one of the ideas that we've had about this. And so we call this a polymorphic network. Yeah.
Define as rural. Like, where did you put the boundary? Did you guys like our suburbs considered rural in your analysis? Like, do you have a real world picture of that?
Yeah. I think it's really hard to. You can sit down and write a line in the sand and say if you have this many users per square area, we'll consider that rural, as opposed to not. But that's sort of.
There's actually a definition. I used to live in Sammamish. I just moved to Bellevue. And Sammamish was very built up. It was called rural.
Oh, it is rural?
Yeah. I don't know now if it's changed now. But
the village of Sammamish.
Yeah. It was
really rich farmers.
So
grass, lawns in their
get those definition from postal services. If you sort of talk to them or ask them, whatever, they definitely have a notion of what constitutes rural.
Yeah, and it's interesting. It's actually sort of convoluted, looking at things like census data and how they classify cities versus rural or outlying city-rural areas versus. There's all these categories and they're all related to each other. It's really hard to draw a line in the sand and say that this is the number. But maybe for the postal services usage is. But
here it's really about TV spectrum usage, right?
I think so.
It's really what demarcates your rural from urban.
I think so. But keep in mind, when I say rural, in that respect, amount of bandwidth available, that might not refer to farms. If there's a city with no TV transmitters around it, that's rural for our considerations. I think you'll be hard-pressed to find that, but it could be. So to introduce you to this, what we see sort of as a potential next step for white spaces, an additional application, are this idea of a polymorphic network. And so what we mean by this is that existing APs can control their cell size. We talked about this earlier by controlling their transmit power. You can shrink your cell sizes. Cellular networks do this today. And we've also seen mobile devices that can hand off between different networks operating on different frequencies, going from 3G to Wi-Fi. Your smartphone does that today. Now, the idea is what happens when we have a unlicensed AP that has both Wi-Fi and white space radios on it. we can imagine having a card. We already have our Wi-Fi cards operate at 2.4 gigahertz and 5 gigahertz. Why can't we put eventually someday another radio on there that operates in the white spaces? You can envision this. And now once you have networks built like this, the network can make power controls and power control decisions, and it can also change the operating frequency. And when you do that, when you make those decisions like that, you have this order of magnitude change in the area of coverage. So that's really interesting. What can you do with that? And so one of the ideas that we had for this polymorphic network is that if you dynamically turn on and off interfaces in some smart manner, and to be defined later, in response to changing user demands. So people come to the Microsoft campus during the day, and maybe they go home at night, but they're working on SIGCOMM papers, and maybe they don't. And so during night, you don't need a lot of capacity. But during the day, you need very concentrated capacity for everything that everybody's doing. And again, even during the day, people move around. They go to conference rooms and things like that, and they need concentrated bandwidth in one area. So the idea is that if you have a network that can adapt to these demands, adding this additional variable frequency changes things a lot. And we're doing this in an unlicensed spectrum and an unlicensed device, so we assume it would be cheap and easy to deploy. Yeah.
Is the coverage area of the network also going to change, or is just that where capacity is allocated is changing?
Yes. so let's get to that. I think if you still have that question, bring it back up. So here's just an example of how this would work, how we envision this would working. So we have a bunch of users, 1,000 users concentrated in some 10 by 10 kilometer area. They're at a concert, so they're all centered in the center where the singers are, something like that. So this is a Gaussian distribution of users with some guys thrown in the boundaries to ensure coverage. So if we wanted to cover this demand with a traditional Wi-Fi network, and our users turn green when they're happy, when they're satisfied, in this case, we would have to deploy 515 Wi-Fi APs. Do it regularly, a grid pattern with no other knowledge about the environment. We can satisfy their demand, and we can power control each of those, to shrink and to serve the users that are in its radius of coverage, things like that. So that's why some of those are small, some of them are big. If we had APs, on the other hand, that were able to dynamically change their range on this order of magnitude that we mentioned before, suddenly we have these APs so not changing the locations of the APs, but now we're allowed to turn some off, and others we're allowed to turn white space interfaces on at the same time. And so if we, in this plot, we have all the black circles are Wi-Fi, just Wi-Fi. All the green circles are just white space. They're operating on just white spaces. And all the red ones are Wi-Fi plus white space, very high concentrated capacity. We're turning on additional bandwidth for those areas to serve those users. And when we do that, we go from 515 active APs to 44. So that's pretty big. So this is, I think this is pretty promising right there, that we can reduce the number of active APs just by having these additional network interfaces available to us. One of the qualifications, the reason why this is still under consideration is that this is not strictly true. APs right now, if they're being underutilized, go into a low power idle mode, something like that. So we would have to account for that and see how that changes this. But we can see this potential that if you can just turn APs off and then turn them on later during the day, you might be able to get some good amount of power savings that way. And so that's a very interesting problem. So it's an open problem. Now the idea behind the polymorphic network, just before we leave, is that this network is going to change in response to user demands. So the concert is over, people are going home, and so starting at the top left, we reduce the number of users by 30% in each case. And the network at every time instant is going to make a new decision about what interfaces to turn on or off. And as we do that, the number of cards active, and I'm splitting white space and Wi-Fi separate in this case, number of cards decreases, so the amount of power that you're using to serve all of your users decreases as they go away. And so you can adapt your network coverage range and capacity to whatever it needs to serve at that point in time. So that's very interesting. So you still maintain connectivity. You could have this potential for huge energy savings. It's unclear, and I think it's interesting that this could be a value add for existing deployments. If you just add another network card that works in the white spaces to existing Wi-Fi deployments, suddenly your network becomes a polymorphic network. So I think that's very interesting. But there's a lot of work needed to understand this, sort of quantify the gains that you get there, if any. So just to finish up, guys, I think I think I've convinced you that white spaces are a new and improved ISM band. If you weren't already convinced. And I think we demonstrated that there are very high potential gains in terms of this coverage versus deployment cost ratio that you can get with white spaces in some situations. Like we said before, we need a careful understanding of when, in what situations this holds true. But we also demonstrated that if we start looking at new types of networks that we can deploy with white spaces, using the entire range of bandwidth available to us, I think the possibilities of your network deployments gets pretty exciting. You can save a lot of energy, save a lot of money in terms of operating costs, things like that. And I think since this is a relatively new area, that the next couple of years are going to be pretty exciting. We'll see if this white space breaks out into common use, and I think it will. I think it has to.
Foresee, especially your polymorphic network thing, reminded me of a whole bunch of discussions that were going on when mesh was all the rage. And do you see white spaces perhaps reviving the old mesh dream of the problem that everybody always had with deploying mesh was if you wanted to make mesh this sort of organic thing where people could go down to their Best Buy, buy a mesh router, bring it home, set it up, and give them internet connectivity. And then as more of their neighbors did it, they would add in and possibly increase the total bandwidth. But the problem was that the very first person who went to Best Buy and bought it and brought it home, they wouldn't get connectivity because they were too far from the nearest next hop. And if you had a longer range radio that would guarantee that the first person who brought it home would at least get some connectivity, then you could, that's a big game changer there, right?
Yeah, I think it is. One of the issues with mesh is that as you start hopping over and over and over again, every single time you do that, that's additional time spent in your transmission. And
you don't want to do more than 3 or 4 hops.
Yeah, as soon as you do that, you throw out real-time applications out the window. It's really hard to support that with the available bandwidth. So I think it is interesting that white spaces let you go further with each hop. So.
But I think what's key here actually is that you can reach a base station that's deployed in a single hop. Because,
I see what you mean.
Because otherwise, the people going to Best Buy, the first guy who goes to Best Buy isn't going to get connectivity if he's more than one hop away, right? So the key difference here is that you have at least one radio on the device. Again, you'd have multiple radios operating in different bands, but you have to have at least one radio on the device that at least provides, even if it's very low bandwidth, at least some connectivity.
Yeah, I think that's really interesting. And we would assume that radio is white spaces. Yeah. So no matter where you are, you can get white space access. And that's almost similar to what we see with 3G networks today. Wherever you are, you can make a phone call, but trying to watch a YouTube video, you might be out of luck in most cases. And so it's similar, but on the other hand, we're operating on unlicensed frequency bands. So you have communities that can deploy those networks. But that is true, that if you have both interfaces on the same device, there are a lot of opportunities for innovation there. So I think that's very interesting, especially since whereas 2.4 gigahertz and 5 gigahertz, they're not very different in terms of their propagation characteristics. And transmit power is an issue, but again, they're not very different. We tend to lump them together. White spaces is radically different. And so I think that's very interesting. Yeah.
Okay.
Thank you very much.
I think we've asked enough questions. Thank you very much.